Hey everyone, this is the fourth Physics 2211 lab oscillations. All right, so the fundamental principles we will be observing in this lab are Newton's second law, which is that the net force is equal to the change in momentum divided by the change in time. In this lab, our net force is equal to the force of the spring plus the force of gravity, or that F net is equal to Ks plus mg. We're also using the energy principle, and the energy principle says that the change in energy of the system is equal to the work done by the surroundings. In this case, we're choosing our system to include the mass, the spring, and the earth, and our surroundings to be nothing. So because there's nothing in our surroundings, no work from the surroundings can be done on our system. And so our equation representing the energy principle is the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy is equal to 0. All right, so the purpose of this lab is to observe and measure the motion of a mass swinging in an arc while oscillating on a spring. We're going to analyze this motion using Tracker and model it using Python on GlowScript. Our goal in this lab is to determine if this model we've created in Python satisfies the energy principle, which again is the change in energy is equal to the work from the surroundings. To preview our results, we found the total change in energy of the system remains equal to 0, meaning that the energy principle is satisfied. All right, so our initial conditions include the mass of our object, which is 0.402 kilograms, and we determined this from the pre-lecture video for the lab. Our initial position is minus 11 in the x and minus 0.634 in the y, found using Tracker. And our initial velocity is 0 in the x and 0 in the y meters per second because our object is being released from rest. The initial spring length is given in the video, and we are able to solve for the spring constant using our observations of the mass oscillation. Since we know that the period is related by 2 pi times root m over k, we can solve for k knowing m and counting the amount of time taken for an oscillation. We can also solve for the relaxed length of the spring as we do on the bottom right using the fact that the object initially starts at rest and is at static equilibrium, and also substituting our given values from the video and the k we previously solved for. All right, so some code. Our initial conditions are the mass of our ball, the ball's position, and the ball's velocity. We've also got our time t, our delta t, and the gravitational constant 9.8 meters per second squared. We've included our spring constant, the rest length of the spring, and we've also calculated L hat, which is the vector L over the magnitude of L. The stretch of the spring is S, the magnitude of L minus the rest length of the spring, and we've calculated the initial kinetic energy, initial gravitational potential energy, and the initial spring potential energy, which when summed up gives you your total energy. So our objective here is to calculate our force of gravity and the force of the spring to basically calculate the net force. And from the net force, we can calculate the velocity and position using the position and velocity update formulas. And so afterwards, since our position is changed, we have to update the spring force, and that's what's happening on the last 3 lines on the bottom left. We're also calculating the change in energy, which we do on the right with our delta K, delta UG, and delta US, and delta E. All right, so moving on to the difference between our observed results and computational results for the motion. As you guys can see, our model does a pretty good job of representing the actual motion, but there are some differences, and this can be attributed to the fact that our experiment is not a closed experiment, meaning that it didn't occur in a vacuum, and there are other forces besides our spring and gravitational force that are affecting our system. So while our model might not be perfect, it's pretty accurate. All right, so back to the main question, does the motion in this experiment satisfy the energy principle? And the answer is yes. We've used the energy principle to explain why. Again, the energy principle says that the change in energy must be equal to the work done by the surroundings. However, in this case, since we chose the surroundings to be nothing, we expect that the change in energy is 0 because the work done by the surroundings is 0, and this is shown by the graph. The horizontal orange line is delta E, and it's constant and equal to 0. All right, so the last thing we need to consider is the oscillation in both the x and y directions. We calculated the time it took for 3 oscillations to occur and divided it by 3 to get a more accurate value for the period. We then calculated the k constant using the relationship we know between the period m and k, which is that the period is equal to 2 pi times root m over k. The K constant is different for the X and Y directions because the periods in the X and Y directions are different, possibly causing large discrepancies in our model. So it's important to figure out which direction you're using to calculate your K constant. All right, that's all I have for today. Thanks for watching.